Alright, we'll be looking at the Poisson distribution. And the Poisson distribution is used to model rare events, that is, events that rarely occur. A rare event is one which has a low probability of occurrence. And so, examples of events that follow the Poisson distribution are the number of misspelled words in a 1,000 uh, page book, a book that has 1,000 pages, the number of defects on the finished product, the number of infected plants um, in the feed, so the number of infected plants in the feed. So assuming you have a farm, you plant, you maybe you planted something and then they are growing and then you want to check how many of them are infected. All right, so the number of deaths in the country by any disease or natural calamity, and then focal by unit time. These are examples of events that follow the Poisson distribution. The PDF for the Poisson distribution is lambda raised to the power of x multiplied by exponential is equal to 2.7 281 like that. So approximately we just put this at 2.783. You can always get that with your calculator or with a program, a computer program. So approximately it's equal to this. And lambda, okay, so e raised to the power of, lambda raised to the power of x times e raised to the power of minus lambda divided by x factorial. And lambda is called the average. So it's a parameter and it's called the average. All right. So somehow you can, or in some way you can find it from what you have, the kind of event you have. All right. So in that case, so we'll look at some of the properties, or rather conditions for the Poisson experiment. The conditions. Number one, the experiment consists of counting the number of events occurring in a fixed interval of time or space if these events happen with a known average rate and independently of the time since the last event. So we look at something like this. What we are trying to say is that we have a lambda and we will have it to be something per another thing, something happening per another thing. So another thing. So then when we have that, then we have an interval. Okay, perhaps in a 3, the interval may be 3, the interval may be 2, maybe 1, maybe 5, maybe. It depends on what we really want at any point in time. For instance, we may have 12 calls per hour. And so somebody may say, okay, maybe in an interval of 2 hours, okay, somebody may say, okay, no. Per hour also means minutes. So we may convert to, so somebody may say maybe in 4 hours, like that. So this is just what we are trying to say. And it may not be necessarily like this. It may be, it may not be calls per hour. It may be maybe errors per book, per page. So, and then we may be saying we want some other thing. So it may just be something like this, error per page here, like that. So it depends. So we are saying it may be it may be occurring in a fixed interval of time or space if these events happen with a known average rate and independently of the time since the last event, so that the number of events occurring do not depend on the last time it occurred. If it occurs now, it's independently of the last time it occurred. So we don't, that's what we are trying to say there. Then going to the second one, the probability of the event remains constant for each interval of equal length. So as long as you have an interval of 3, for instance, you keep having the same probability as long as lambda does not change if your x doesn't change. All right, so the number of occurrences in one fixed interval is independent of the number of occurrences in another fixed intervals. So there is no dependence between them. Then the random variable x denotes the number of occurrences in the interval of interest. So that's it. So those are what make for your Poisson experiment. All right, in that case, okay, let me leave this. Let me need it. So in that case, we can move forward. Now we look at the properties of the Poisson distribution. Now the expected value of x is the same thing as the variance. So the mean is equal to the variance, and that is equal to lambda, your average rate we talked about the other time. Now the average number of occurrence per unit time or any other specified measure is known. So you need to know lambda. There is a non-zero probability of non-occurrence of the event in any specified interval. We are saying that the probability of an event occurring in any specified interval is known and it is not zero. All right. The random variable x denotes the number of occurrences in the interval of interest, and x can assume values 0, 1. So we're saying that the event may not occur. It may occur once, it may occur twice, and it may occur 3 times, 4 times, like that. Okay. Within the given interval. So it may occur, it may not occur within the given interval. It may occur once within the given interval. It may occur twice within the. So when the expected value, that is expected value of x, when the expected value of x, which is equal to np, is less than 5, we have lambda to be equal to np here. Then we are saying the Poisson distribution approximates the binomial distribution. Okay, I'll come again. When lambda is equal to np and it is less than 5, so lambda is less than 5, we are saying that we will have an approximation of, okay, the Poisson distribution will be approximately equal to the binomial distribution. So actually, in general, the Poisson distribution can be used to approximate the binomial distribution when p is very small. When p is small and n is large, and n is large. So then the Poisson distribution approximates the binomial distribution. So in another way, you could just say when the expected value of x, which is equal to the average rate we have, lambda is equal to np and is less than 5, then the Poisson distribution can approximate the binomial distribution. All right, so we'll move on. Let's see some examples of what we can do with the Poisson distribution. Now, suppose that we said, okay, initially we had talked about the fact that the Poisson distribution actually deals with rare events. Now, assuming we have 135 typographical errors randomly distributed in a 4,500 page manuscript, what is the probability that any given page has 4 errors? has 4 errors. Now, in order to find that, we need to know certain things. Number one, we were told that the mean number of errors, okay, we were told that there are 135 typographical errors in 1000 in 4500 pages. So you need to take care of that, this and this. So that means our average rate is going to be 135 divided by 4. So for every 4500 pages, we are expecting 135 errors according to what we are given in the data. And when we do our mathematics on that, we get 0.03. So that means 3 errors per 1000 page, I believe. So the same thing, 3 errors per 1000 pages. Alright, now so it means that our X is distributed Poisson with an average rate of 0.03, and then we have the probability of X to be equal to 4 to be equal to what we have here, and that's just by substituting lambda and X. And then when we do that, we have 3.275 times 10 raised to the power of minus 8. Alright, this is approximately close to 0. This is very close to 0, so there's practically no chance that you will have up to 4 errors in a page. That's what we are saying here. That's what this means. So, and then we're told to find the mean and the variance of the number of errors. And for the Poisson distribution, according to the properties we checked, the properties we looked at, rather, we know that okay, the mean and variance should be equal, and that's the reason why we have it. Okay, we have them to be equal here. So the expected value of the number of errors is something as the variance of the number of errors, and that should be 0.03. Alright, so now we come back to this. So 0.03 errors per page. Now we come back to this. Suppose that the mean number of phone calls arriving at the Coca-Cola head office in Ilorin is 24 calls per hour. What is the probability that no call will arrive in a 2-minute period? So this is the interval of time we're having. More than 2 calls will. So we are also to find the probability that more than 2 calls will arrive in a 10-minute period. And we have the probability of X equal to X to be this. So the PMF of the Poisson distribution, and we have X to be equal to 0, 1, and then like that. So now we have a lambda because we have 24 calls per hour. So we have a lambda to be 24 calls per hour, but because we are concerned about a 2-minute period, that's the interval we're giving, we will multiply that by 2. So, and since we have this to be minutes, we need to change this to minutes to bring about uniformity, or otherwise you need to change this to hour. And if we are doing that, whichever way we do that, we end up having 0.8. Now, so we have 0.8 calls. We've changed this to minutes, and so we now come here. Probability of X equals to 0 will now be, so substituting lambda value in in this expression, and putting X equal to 0, we get all of what we have here. That becomes 0.4493, and then that means that there is approximately not 50% chance, a 45% chance. How do I get 45%? This is approximately equal to approximately equal to 0.45, which I would not want to write, but since I'm saying approximately, so I can use that. But it's always advisable to leave your answer in four decimal place. You just have four decimals like your or four figures here, four after the point, 4493. All right, so if I multiply this by 100, it gives me 45%. So that's what I've done. All right, so this means that there is a 45% chance that a page will contain up to not four errors, sorry about that, contain no error. We're not talking about error this time around. Sorry, I think I just had a copy and paste kind of stuff there. So, which means, let's interpret this the way it should be. We're talking about phone calls. There's approximately 45% chance that no phone call will, let's see, will arrive. Will arrive in a 2-minute period. All right. So this means that there is, well, you may just say the probability that no phone call will arrive in a 2-minute period will be 0.4493. That's also a good way of saying it. All right. So what's the probability that what's the probability that more than 2 calls will arrive in a 10-minute period? And that means that we are looking for more than 2 calls, not at least, more than. So it should be greater than 2. This should have been the case. Sorry. In this case, it should be greater than 2, not greater than or equal to 2, except I change the question. So we should have, this should be greater than 2 because we said more than. So this should be less than or equal to 2. And in that case, we should have one more of this. So that means we'll also do it for x equals to 2 and over 2 factorial, and that should give us 0.1465, and in that case we should now have 0.0183 plus 0.0733 plus 0.1465, and that should give us times being okay. We should have 0.2381. And when we subtract that from 1, we should have 0.7619. So in that case, 619. All right, so this is what it should be, and that gives us our answer. So if we need to find the mean and the variance, okay, that should not be an issue. The mean will definitely be 4. In this case, in number 2 will be 4. The variance will be 4 also. So make your 4 calls, and in this case it will be 0.8. All right, so You may hear something like 0.8 calls per minute, 4 calls per minute, all right, as your average rate. So that is that about that. And it is sufficient to remember that your Poisson distribution uh, can be of many types. So you just need to be careful to know which one you're talking about or what you want to do. So the key to always getting your Poisson distribution right is to remember that the Poisson distribution, number one, models rare event. That's one, and also that it has to do with counting the number of events occurring in a fixed interval of time or space. So, and so please take note of this fixed interval of time. Okay, fixed interval of time or space. So take note of that. And then it can be of a number of types, even beyond what we have here. But bearing in mind that you are counting the number of something that is not so okay. There are not so many of them. They are rare, but then you are counting over an interval of time or space. So examples are the number of misspelled words in a 1,000 page book, the number of defects on the finished product, the number of infected plants in the field, number of deaths in the country by any okay the number of deaths in the country caused by any disease or natural calamity, and phone call per unit time. All right, so phone calls per unit time. All right, so that will be all for the Poisson distribution. That will be all for this lesson.